for done. It is interesting to notice that the application is still running. Notice the server is still back here, but we have the core done. So that means that I can probably still reconnect. Let me try with a small number. And it still works just fine. So it was only that one thread that crashed. So this also gives us some information about this service. We can probably try to attack this service many times without crashing the service itself. Now, there is also the possibility that in the process of doing this, we're corrupting some other parts of the memory, so it may become unstable. In fact, for that reason, before I forget, I'm just going to stop this server and restart it, so that if the memory has become a little bit unstable, I don't have to worry about it changing the results later. Well, let's come back over here with our fuzzing example. So we've now managed to get it to crash, and we've created this core dump. But what can we do with that? Well, the core dump itself can be opened up using GDB, or a debugger. So let me run GDB. I'm going to give it the -core option and have it open the core file. Now, as soon as I open it, you'll notice here at the very bottom, it tells us that this program terminated with a segmentation fault, which means that we tried to read or write in or out of a segment that we don't own. That's a sure sign that there has been a stack overflow of some kind. And then down here, it shows us the instruction where it exited. Well, this is interesting. Notice what the problem is. Apparently, let me show the registers. Just show InfoReg, excuse me. If I take a look at the registers, I find that the EIP, the instruction pointer, contains 0x41414141. Now, you may not recognize those hexadecimal characters, but what they actually represent are the uppercase letter A. That's exactly what we sent with our Perl script. So at some point, we managed to overwrite the instruction pointer. And you may also notice that it's also in the EBP. That's the frame pointer that we overwrote. So we've managed to change data on the stack so far that we actually overwrote the instruction pointer. And this is what created the segmentation fault. Overwriting the stack didn't do it. What created the segmentation fault is that after returning, it tried to execute code at a region of memory outside of our program's memory space. That's what created this segmentation fault. Now that we've created the segmentation fault, though, we have some other questions we need to answer. What we need to know is where exactly is this buffer and how big is it? We know there was a stack overflow. We know we've successfully overwritten the return value, but where is the buffer and how big? Well, how can we find that information? Now, what we could do is we could begin trying to poke around in the stack. So, for instance, we could try to display information found in the stack. We'll just use the value that we find here to discover what's in the stack, BFFFED30. And I can say, oh, wow, okay, the whole thing is filled up with 4 ones. Let me print more than this. Let me come back here to 0, 0. Oh, we're still all full here. Okay, so I can begin to poke around here and see, well, where does this start? Here's where it starts. And then through trial and error, I could try to run this multiple times to try to figure out exactly how many characters does it take before the instruction pointer is overwritten. But you know, that's a lot of work, and there is a much, much easier way to go. It turns out that there is a very, very handy tool that's part of Metasploit. Metasploit includes this handy function called pattern create. What pattern create allows you to do is tell it to create a pattern of characters. You can see an example here. I can take a look down here. I've got the Metasploit framework installed over here. We can run pattern create, and it will ask you first of all to give it some parameters here. It would like to know what length there is. Now you can also specify a set of characters. That can be important if they are limited on what kinds of characters you can use. For us, that's not a concern right now. So I'll just say I'd like a pattern of 100 characters. It will then create for you a pattern that you can use as your input into the application. For instance, over here in this machine, I've copied a pattern of 2,000 characters. So if I just more this, you can see these are all of the characters created by pattern create. What I can do with that information is take that pattern, just as is pictured here, and I can send it through Netcat to that server. Let's give it a try. Now first, I'm going to remove the old core dump so I don't end up with any confusion. And I'm going to cap the 2K pattern through Netcat through the service. This is perfectly expected. The program still crashes. We have a new core dump. And when I open this one up, notice the value found here, 65413165. What I can do with that is use pattern offset. Pattern offset is another tool found within Metasploit that allows us to discover what the actual size of the buffer is by analyzing that pattern. Again, to use it, you just run pattern offset, and you can see what the parameters here are. It wants you to find the search term. So we're looking for this value that came back. We're looking for the value that was found, and you can see it here, found in the instruction pointer. So let's give that a try. 0x65413165, and then the size of the pattern you sent. We sent a pattern of 2,000 characters. It immediately comes back and tells you that buffer is 124 bytes long. Now, let me just clarify. It may be that it's not exactly 124 bytes long. What may be happening is that's how much space there is from the beginning of this buffer to overwriting the instruction pointer. There may be other values on the stack in between, so this buffer may not be 124. In fact, we know for sure it's not, because before the instruction pointer, we would even have the stored frame pointer. That's another 4 bytes. So maybe it's 120 bytes. But could there be another buffer or some integers or some other value stored there? Absolutely. What's important, though, is that we know, as it says here, we have 124 bytes to work with between the beginning of this buffer and the instruction pointer. That means that when we look at the registers now, in this same core dump, I can see where the buffer starts. Here's where the stack pointer is as we're entering this particular piece of code. So before the exploit has actually happened. So if I dump out here now, let's dump out 64 bytes. And let's go from 0xBFFFED20. Well, this is a little bit harder to see because we've got the pattern in there, but I can now discover where exactly this buffer begins. So the buffer begins back here and extends down through where the instruction pointer actually resides on the stack. So I can now easily calculate or know where to start from. I also now probably know a usable return address, provided that address-based randomization is not turned on. Now, I'm not going to talk about that a whole lot here. It's one of the different strategies that's used to protect our stack from stack overflows. We've actually disabled some of those safety precautions just so we can illustrate this problem. Now that we've got some stack contents, we know what the registers are, we can now discover how the overflow is really occurring and make some determinations of how to go about attacking it. For instance, if we were dealing with address-based randomization, perhaps we would want to find out what shared libraries are available, and rather than trying to come up with a memory address that we can use, perhaps we would do a return to libc or an arc injection attack. So at this point, we can now begin discussing or figuring out what kind of exploit or how to go about actually exploiting this vulnerability. In our next section, we're going to take a look at a short tutorial on how to write some shell code before we actually go into how you exploit this using Metasploit.